Thank you very much. So whereas the preceding talk focused on on learning models of when best to offload at the level of the object method, I'd like to turn our attention to how we can use some new principled mechanisms to do offloading at such a fine granularity. Now, this is a joint work with my old PhD advisor, Chit-Kwan at Harvard. So just a bit of background. It's only really been within the last few years that these three forces, device, cloud, and network, have kind of converged to the point where offloading can actually be used to deliver performance to mobile applications. Of course, there's been a massive proliferation of mobile devices, and we're constantly asking these devices to do more and more complex tasks with less and less battery usage. And so the demand for better performance is certainly there. Meanwhile, cloud providers have made it pretty frictionless to take advantage of economies of scale and dynamic provisioning. And at the same time, networks have kind of come, both wireline and wireless networks have kind of come to the point where bandwidths and latencies are kind of at the cusp of being able to support this kind of tight coupling between device and cloud infrastructure. Now, offloading, of course, is a pretty complex problem, and there's, of course, plenty of great work that's been done by the distributed systems community that's very relevant. But in this work, our approach is to take some of these familiar ideas and, together with some new algorithmic techniques, see if we could make fine-grained offloading not only highly responsive, but also practical. So how do we do that? We're actually going to just restrict ourselves to a very, very simple but tightly coupled distributed shared memory system that spans a mobile device and a cloud server. On the device, we have this memory block that's tightly and continuously replicated to the cloud. And that means that any object that's allocated out of this memory block here also has a replica that's on the cloud. And as a result, any method invocation on this object can also be offloaded in principle and serviced by the replica that's on the cloud server. This basically means that we get to sidestep something like object marshalling, which is everybody knows is pretty costly. Now, we characterize this kind of offloading as dynamic and fine-grained, but why do we really emphasize these two properties? Well, let's think about how we actually offload computation today. Basically, it's web services, right? Using this approach, we would partition our application into device-specific or cloud-specific pieces at compile time. But this is really hard to generalize to assigning work to the cloud in a dynamic way during runtime. But under the more dynamic rubric I've just sketched, not only is offloading the arbitrary work at runtime possible, but it becomes kind of a way to optimize resource utilization at runtime. So a simple example is, if I'm low on batteries, I might prefer to offload a little bit more work to kind of stretch out the battery budget. So as a result, we actually want to offload at a very fine granularity so that we can have the flexibility to take advantage of even small opportunities in optimization. So at this kind of resolution, offloading apps will feel more responsive to the end user. And this is especially true when we have failures in the offloading task and we need to do a local restart on the device. Well, of course, this is great and all for the end user, but we also care about cloud providers. And for cloud operators, offloading at this granularity is also good because it provides this kind of class of small, steady stream of small workloads that you can use to plug holes in your utilization, right? But we're able to do this while maintaining kind of like a low latency service for the end user. All right, but doing all this is actually pretty hard. So there's latency is a central concern because it dictates the task granularity. So the lower we drive latency, the finer grain tasks that we can actually offload. So for instance, if a replication update takes like 5 seconds, then any task that completes in fewer than 5 seconds would never benefit from being offloaded, right? Bandwidth is, of course, another issue. The optimal thing when we're doing this replication update is to figure out the delta encoding, right? And then compress it and then send it. But this is actually not that easy. We can't use transaction logging because memory I/O doesn't really work like that. And we can't really use things like rsync because there's actually kind of non-trivial latencies and overheads associated with that. In any case, whatever we decide to send, we actually should be compressing it as much as possible. But of course, compression isn't free either. So in some cases, it's actually quite computationally expensive. So at the end of the day, also none of this work that we're doing to support the offloading can take any more battery budget than what would be used to do the work on the device to begin with, right? So it's all kind of a jumbled mess. And optimizing for these constraints is not straightforward because these constraints are not independent of each other, right? For instance, battery is a function of compute, and latency is a function of both compute and bandwidth. And so we're bound to have some sort of trade-off. And the trick here is to find a replication method that gives us a good enough trade-off to support this kind of fine-grained offloading. So it turns out that compressive sensing can help. Compressive sensing is an efficient random sampling technique, and here's how it works. So suppose we have this real valued signal here we call x. We say that its sparsity is k. K is 3 in this case because there are 3 non-zero elements in the vector. So compressive sensing basically works by randomly mixing the signal's elements into so-called compressive samples, such that each of these samples contains some information from each element in the signal. And this is done by random linear projection into a lower dimensional space through this linear operator phi. The dimensionality reduction that results is from n to m, and so we have compression, right? So now it turns out that compressive sensing theory tells us that if m follows this interesting bound here, that with high probability we can actually reconstruct x from y, even though this system of equations is underdetermined. So how does this help us? Well, the key insight here is that writes to memory actually constitute a sparse signal that we can compressively sample, right? Writes to memory equals deltas to memory. Now this admits an efficient and low latency replication scheme, which we call compressive replication. So here's how it works. At time zero, we have the device and the server, and they both start out with their memories synchronized. The byte values here are denoted with x0. And both device and server also know the sampling matrix phi. So the server can therefore calculate the initial samples y0. Why not? So at a later time, t1, there's been some writes to memory, okay? And so there's a new state on the device, which we denote x1. And the task now is to bring the server up to date with the device. So what do we do? The device first calculates samples y1 and then transmits these samples to the server. Now that the server has both samples y0 and y1, it can calculate the difference, which we call y prime. And after some simple algebra, we actually have this expression, which is y prime equals phi x prime, right? Sorry for the math, but I'm sure you guys can handle it. I know you're not supposed to put math on a slide. But the important thing here is to realize that that x prime is key. X prime is actually the delta encoding between my previous state and my current state, right? So this is great because we can actually recover x prime because y prime equals phi x prime is the exact same form of the compressive sensing problem we saw earlier. And we can solve for x prime using known compressive sensing decoding methods like convex optimization, matching pursuit, what have you. So once we have x prime, once we have the delta encoding, we obviously, the last step is to apply the delta encoding to the server replica to bring the replica up to date. So compressive replication has some really interesting characteristics. So first, compressive replication in effect combines both delta encoding and compression in an all-in-one operation. On top of this, it automatically recovers the delta encoding at the server. Now this is really weird, right? Because normally you can only figure out a delta encoding if you have the freshest state, meaning the device should be the only one that can figure this out. But by shifting the work and the responsibility over to the server, we actually have a really big gain, which is we've removed all of the communication cost required beyond just sending the compressive sample, right? Now, furthermore, our codec is also resource commensurate in the sense that we have a relatively low complexity encoder that's on the device, and a relatively higher complexity decoder that's on the much beefier server. Right? This is exactly the opposite case of traditional compressors, where you usually have high computational complexity on the encoding side and lower complexity on the decoding side. And obviously, for traditional compressors, this doesn't match the resource distribution that we have in our mobile setting. All right, so these interesting characteristics actually make it kind of hard to make a good comparison against anything else, because nothing else really exists that is like this. So really kind of like the best comparison we can look at is shipping compressed snapshots of the memory block from the device to the server. And mainly we make this argument because there's no network cost beyond just sending the update, right? So we compare against two popular compressors, Snappy and zlib, and we use the total update latency and the compression ratio as the metrics when we replicate a 64K memory block. So how do we do? It turns out that neither Snappy nor zlib really offer a good enough latency to compression trade-off. Right? Snappy, which is a Lempo-Ziv type compressor, is really fast, but it gives up compression by not doing any entropy coding. So even though it has really low latency here, it actually uses quite a bit of bandwidth. Now zlib is exactly the opposite. Right? It spends a lot of time, in fact too much time, trying to figure out a bit level Huffman tree. And as a result, it uses much less bandwidth, but its 500 millisecond total latency is way too slow to support fine-grained offloading. Now, on the other hand, compressive replication gives a pretty good trade-off. It has the highest compression overall, although, to be clear, the compression ratio is high because we're in effect compressing the delta encoding rather than the full memory block. And we still manage to get a respectable latency. Now, even though this latency is slower than Snappy, the key point here is that it's near 100 milliseconds, which is a well-known threshold for user application, user perception of application delay. So the key point is that compressive replication actually gives us the best of both worlds. It remains possible to offload at this critical granularity, but we're able to achieve a 50 some odd % reduction in bandwidth utilization compared to Snappy. Now this is pretty good, but there's still two more advantages to compressive replication. So it's actually friendlier to other network applications because the compression ratio and as a result the bandwidth utilization is fixed and predictable across updates. And this is kind of strange. This is because our method is actually a sampling operation, right? And the number of samples that we're taking, m, is fixed. It's constant. Now, in contrast, Snappy and zlib are dependent on the Kolmogorov complexity of their inputs. And so these can vary across updates. This also means that our method can, in effect, compress things like an array of floats, which have high Kolmogorov complexity, and therefore confound compressors like dictionary coders like Snappy or entropy coders like zlib. Now, next question, of course, is can we translate compressive replication gains into practical compressive offloading gains? And to this end, we built a prototype platform. We call it UpShift for offloading the work from iOS apps to the cloud. As an example, we ported an open source Chinese handwriting recognition engine to the platform. And this engine comes with a trained SVM for doing the recognition task. And it's this recognition task that we want to offload. Now, we chose this example because each Chinese logogram is written with a prescribed number of strokes. And we use this stroke count as a proxy, as a measure of the complexity of the recognition task in our experiments. So here, this is a screenshot of the app. For those in the audience that are sensitive, I'm sorry for subjecting you to this horrible penmanship. But basically, the way that this works is that I write on the screen with my finger, and the app captures the strokes as I'm writing and saves it in memory, in an in-memory object. And this object is actually allocated from this special replicated memory block. And so as a result, in the background, the object is being replicated to the server. And when I finish writing, I hit a button, and it fires off this evaluation method, which my platform then transparently directs to the server replica. Now, our experimental setup mimics a typical usage environment. Our device is a third-generation iPad. It's on Wi-Fi in a typical office setting. We have a mean RTT of 19 milliseconds to our Amazon server, which is a GPU instance. And we use these instances because we use the GPU to do the decoding for compressive sensing, and which leaves free the CPU to do the actual offloading work. So how do we do? So these performance results are, of course, preliminary and fairly rudimentary, but they show some pretty good potential. Here we're measuring the character recognition time as we scale up the task complexity. And blue is on device, and green is offloaded. On the right-hand side, the red curve shows the speed up, which is just another view of the figure on the left. So for example, for a moderately complicated 20-stroke character, on device takes about 8 seconds. Actually, probably can't point to it accurately here. 20 is probably like 8 seconds there. But offloaded, it takes 1.7 seconds. Right? It's more than a 4-fold increase. And for even more complex tasks, the speed up is even higher. It's like 30 strokes is like 6.5-fold. So in general, on-device execution time scales really poorly with task complexity. And this is representative of a lot of image processing, machine learning, signal processing, recognition tasks that we're asking these devices to do. On the other hand, under offloading, the more complex the task is, the greater the speed up, right? Which means that the execution time remains pretty level. Now, this is really important to end users because they have it's really important to end users' perception of responsiveness, right? Because users usually can't distinguish between what's a difficult task and what's an easy task. And so they typically expect this kind of level behavior. All right, batteries. Do we win? We definitely win. In this experiment, we're using an iPad. We start out with a full charge. And we do 250 consecutive recognition tasks of relatively high complexity characters. Again, the blue describes the on-device performance, and the green describes the offloaded performance. Now, the big takeaway here is that even though compressive offloading uses both the iPad CPU and the Wi-Fi radio, the power that's drawn to do the offloading is significantly less than performing the work on device. And in fact, with the exact same battery budget, offloading allows some 60% more work to be done, which is really great for end users. Now, to recap, all right, we've argued for fine-grained offloading and that an efficient low-latency distributed shared memory can be the basis for tightly coupling a device to the cloud. In fact, the lower that we drive the DSM's replication latency, the finer the grain, the wider range of workloads that we can actually offload. We show that our platform can handle offloading tasks that are about 100 milliseconds, which is a really critical threshold for user-perceptible delay. And we can do all this while keeping the bandwidth low, the compute low, and the battery usage low. And as a result, we've been able to achieve some pretty significant speed-ups and battery savings in a practical setting. But most importantly, and the key takeaway from this work, is that we can do all of this because of the key insight that underpins compressive offloading. Namely, memory I/O constitutes a sparse signal that can be compressively sampled. And finally, I'd like to close with a bit of speculation that our approach can have some implications for emerging ARM-based data centers and emerging x86-based mobile devices. Because when both the device and the server are speaking the same instruction set, compressive offloading all of a sudden becomes a principled way to directly offload machine code to the cloud. And once we have that, the door is really wide open to a lot of things. Thank you.
Hello. I have a question regarding this handwriting example. I don't know whether this example exercises the functionality of delta encoding. Because every time you write a character, right, you just send the image. You never change it.
So the way that it's held in memory is that there's an object that's being updated constantly, right? So that object is replicated.
So just which means that when you write in the character, when you not finish it, it's already sent.
Yes.
Okay. Thanks.
So are you waiting until the character's done and then you're sending the compressed sampling, or you're doing while they're writing the character?
You can do it both ways. The way that we've implemented here is the first way, so that it's easier to calculate the total compute time.
So then the delta you're encoding against is always empty, right?
No.
If you start with a blank sheet.
I see what you mean. No. So as you're writing, the object in memory is being updated, right? As each stroke is being saved into memory. And then in the background, the replication is happening. So when you press the button to do the recognition, there's no more, maybe there's like one more update, but that's it. All right.
Hi, I'm Nitin Agarwal, NEC Labs. I wanted to understand, so in terms of evaluation, you showed a comparison between what if you do everything on the device and everything on the cloud. So you ported the classifier for both like the device and like the instance running in the cloud? Is that how you did that? So it's the exact same kind of classifier running on both?
Right, so basically we ported it to Objective-C,
right, okay.
And we compiled it for ARM and for x86. We deployed, these are like abstracted objects that we can deploy.
So my question was that how big are the models for these classifiers? I mean, how big are the models, the trained models? Are they huge? Are they fairly small?
I think they're actually at least on tens of megabytes.
So they're not big?
They're not too big.
Okay. So
I mean, because it was originally meant for this kind of device, right?
So my follow-up question was that in your work, have you come across, have you developed a sense of what kind of classifiers are better suited for compressive sensing or just kind of better suited for the kinds of applications you have in mind? Or that's like way out?
I guess I can, generally speaking, of course, anything that has a small data input but large compute is good for this kind of thing, right? But I don't think I can say much about specifics.
Good talk. Thank you.
Thank you.
Ymir Vikmansson, Reykjavik University. Thanks for an enjoyable talk. I want to ask a little bit about the sparsity. You have this condition initially that you require the signal, like you require M to be greater than order K log N over K or something like that. And if that doesn't happen, you're not able to actually uniquely characterize the vector itself. What happens?
I've prepared for this
Oh, great.
eventuality.
Yes.
So what happens if there are a lot of memory writes and your signal isn't sparse? Well, you can't do anything. That's the answer. Basically, when it's no longer sparse, you have to fall back to the simple standard snapshotting way.
Okay. How often does this happen? Like if you profile a regular application, does this happen a lot that you get a mem set or something and everything?
Right.
goes wrong?
So like I'm
calloc,
alluding to here, basically this happens when you have large block initialization like callocs. Modern memory allocators don't do this unless you specifically call calloc because they do lazy what is it called, initialization. And when you read a large file into memory, those are the typical cases where this happens.
Okay. And there must be a way to get around that by simply augmenting the way you're looking at memory with those types of operations. So like the delta can be not just the state of memory, but also the operations that just got added.
Right. Yeah, you can just send the operations over.
Exactly.
Yeah.
Right. Would that work, you think? Or?
It works in the sense that like if you have access to that layer of the OS,
Okay.
for instance, then you could do that.
Okay. So if you hook into the memory layer or something.
Right.
Yeah. Okay. Thank you very much.
Wow, so many
So
questions.
just a quick observation. It seems like one useful side effect of this, a potential side effect would be that you could keep like an audit trail on the server of all these operations. So just observation.
Right. You could basically do replay. Yeah.
Do we have the third speaker here?
I'll be at the happy hour, so please come find me if there are additional questions.
Yeah,
Okay.
one more very quick question. Junji from Toronto. And I'm just wondering how much the server does, like the extra cost for server?
Zero.
Zero.
I mean,
mean-
these jobs on the server are basically no ops, right? It's microseconds to do. Okay, sorry.
So did you
Maybe not
actually-
microseconds, but maybe at least tens of milliseconds or hundreds of milliseconds. So it's like,
Okay. So, but you need some, server setup that is waiting for the load to.
sure.
to
I mean, the
service
point
out.
is that the service has two pieces, right? There's a cloud piece and a
Okay.
and a
Okay. Thanks.
mobile piece.